Hi everyone, thank you so much for joining me again today. We are looking at maths and we are looking at grade 11 probability. What we're going to do in today's lesson is go over some of the big concepts that you guys need to know for your final exam. All right, let's get straight into it. So we've asked the question, what is probability, many times, and all of you by now should know that probability is really all about chance. So it's really what we're studying is how likely that something's going to happen. So when you watch sports and your favorite team plays, you don't know really whether they're going to win or not. Maybe based on past experience, you can tell that they're better than the other team, but you can never tell what will happen on the day. So that uncertainty is what probability is all about. Okay, so when the weatherman says there's a chance of rain tomorrow, you may or you may not end up getting wet. So certainly there's uncertainty all around us. Did you hear that? Certainly there's uncertainty. So many events cannot be predicted with absolute certainty. The best we can do is to say how likely they are to happen, and this is what we call probability, and that's the big thing that we're talking about today. So we get this thing called experimental and theoretical probability. What is experimental probability? What is theoretical probability? Theoretical probability is all about using a formula to calculate the probability of an event happening. And experimental probability is really about doing experiments. We also call it the relative frequency. You do an experiment, you list how many times an outcome happens or how many times outcomes of an event happen, and that's called your experimental probability. So for example, if we toss a coin, say 100 times, how many times will heads come up? We can either calculate this using theoretical probability and a formula, or we can actually perform the experiment, toss the coin 100 times, and then record the outcomes. So really theoretical probability is all about using logic and a formula. Now remember that whenever we're talking about probability, we use special words, and we often talk about events. An event is all it is really is just one or more outcomes of an experiment. The total number altogether of possible outcomes is called the sample space. So for example, if I toss a coin and I'm recording how many times am I getting a heads, then heads will be the event. Your outcomes will be heads or tails, because those are the two things that can happen when you toss the coin. And then the sample space will be a collection of all of the outcomes in your experiment. So the number of elements in a sample space, we denote it as n of s, the number of elements in the sample space. And when we work with theoretical probability, we use a formula, as I said. When all possible outcomes of an experiment have an equal chance of occurring, that's when we use this formula, and you guys should be familiar with this by now. The probability of an event E is equal to the number of ways that E can happen. So the number of favorable outcomes, which we also call the number of ways that E can happen, divided by the number of possible outcomes, which is the number of elements in your sample space. Okay, we will go into using that formula just now. So by using theoretical probability, the chance of getting a heads when we toss a coin 100 times is 50. So that's if we actually just use that formula, number of favorable outcomes divided by number of possible outcomes. But when you actually do the experiment, you may record 48 heads or 55 heads or 52 heads, really any number, but it should be something quite close to 50. So experimental probability is found from the results of an experiment that's been repeated many times. You will find that the more times the coin is tossed, the more accurate the probability becomes of getting whatever event you are interested in, and in this case it was getting a heads, the closer that theoretical answer will be to your experimental. Okay, so the closer the experimental answer will be to the theoretical answer. So in other words, this answer from doing the experiment will be closer to the answer that you get from the calculation if you repeat the experiment many times. Okay. Now, there are some key ideas that we talk about when we discuss probability. One of these is dependent events. You will remember that events are dependent if the outcome of one event influences the outcome of the other. Now think about this. Say in your lunchbox you've got 2 apples and you've got 1 banana. When you eat one of the fruit, so it's lunchtime, you're going to eat one of the fruit, it will then reduce the number of choices you have when you eat a second fruit. So remember, you've got 3 fruit at the start. You eat one of them. It doesn't matter which one you eat. But straight away, once you've eaten the one, you no longer have 3 fruit to choose from. You've only got 2 fruit to choose from. So the fact that you've eaten one has changed what's going to happen the second time you choose another fruit. So events are dependent if the outcome of the first event influences the outcome of the second event, or the second event influences the outcome of the third event, and so on and so on. Okay. Independent events are just the opposite. So they are not affected by any previous event. So for example, if you toss a coin and you toss it many, many times, each time you toss the coin, say a tails comes up the first time, that coin didn't know that it came up as a tails. So therefore, the next time you toss the coin, it might still come up as a tails. We don't know. So those events are independent because the outcome of the first event does not influence what will happen the next time around. Okay. When we talk about independent events, we use something called the product rule for independent events to test if the events are independent and to calculate the probability. So if you have 2 independent events, A and B, then the probability of A and B is equal to the probability of A times the probability of B. Okay, and that's only if the events A and B are independent. Another important concept that we learn about is with or without replacement, sampling with replacement or without replacement. So say that a bag contains 5 red buttons and 5 blue buttons. Say we remove a button from the bag, we record its color, and then we put it back into the bag. That act of putting it back into the bag means that we have not changed the number of buttons there are in the bag the second time we make a choice. So we have 5 red buttons and 5 blue buttons. We still have 5 red buttons and 5 blue buttons if we put the first button back. Okay? That is what we call sampling with replacement. So we're replacing the item that we took out the first time. If we do not put that first button back, then that is called sampling without replacement. And that's what we call dependent events. Okay? Now, unions and intersections are something you would have heard about quite a bit when you study probability. Basically, when more than one event happens at the same time, we get combinations of outcomes, and this is what results in unions and intersections. A union of events is the set of all outcomes that occur in the events. So we use either A or B to denote that to tell you that you are to denote that you are working with a union, or you use A, U, B, A union B, and you can see that that symbol looks like a union looks like a U to tell me that I'm dealing with unions. So, say for example, we have the sets 1, 2, 3, and 5, and I've got another set 3, 5, and 7. So that is set A, and this is set B. The union of A and B, so A union B, will be all the outcomes that are in both sets. So my union would be 1, 2, 3, 5, and 7. 1, 2, 3, 5, 7 is the union of A and B. The intersection, on the other hand, of the events is the set of all outcomes that occur in both events. So if we look at set A, I see that 3 and 5 occurs in A, and then 3 and 5 also appears in B. So therefore the intersection, which we write as A and B, or A inverted symbol U, you can see it looks like an inverted U, A and B, so the intersection would be 3 and 5. So it's those elements that occur in both sets. All right, guys, A big concept that you learn about is the addition rule for probability. So you can calculate the probability of the union of two events using this addition rule that says the probability of A union B, or if you prefer to use words, the probability of A or B is equal to the probability of A plus the probability of B minus their intersection. So using a probability symbolism, we see the probability of A union B, or probability notation, probability A union B, or you can have this as A or B, is equal to the probability of A plus the probability of B minus the probability of the intersection of A and B. Now, when that intersection is 0, we get a special case where we are calculating the probability of the union of mutually exclusive events. Now, what is mutually exclusive? Another word for mutually exclusive is disjoint. So basically, two events are mutually exclusive if they cannot occur at the same time. So for example, you cannot be 20 years old and 23 years old at the same time. Those two things cannot happen at the same time. They are mutually exclusive. It cannot be day and night at the same time. That's mutually exclusive. Okay, so think about what are other events that are mutually exclusive. Think about that as we go into a break, and we'll discuss more about mutually exclusive events when we come back. Welcome back, everyone. So before the break, we were talking about mutually exclusive events, which are also called disjoint events. And basically, we said that those are things that cannot happen at the same time. I asked you to think about other mutually exclusive events, real life events that you could think about. For example, it cannot be day and night at the same time. Now, another way of saying that two events, A and B, are mutually exclusive is to say that their intersection, or the number of elements in their intersection, is 0. Okay, so another way to state that we're dealing with mutually exclusive events is to say the number of elements in the intersection A and B is 0. We have a special name for a set with no elements. It's called the empty set, and we denote it by that symbol, that empty set symbol. It almost looks like a 0 with a line through it. Okay, so there are no possible events in that sample space where there can be an intersection, so therefore the probability of the intersection is equal to 0. So what this leads to is an interesting then derivative of that addition identity that I showed you before. So the addition rule for two mutually exclusive events is the probability of A or B is the probability of A plus the probability of B. So really it's just a special case of the rule probability of A union B equals probability of A plus probability of B minus the intersection. It's a special case because what's happening is this probability here is now 0. Why is the probability of the intersection 0? Because there are no elements in the intersection. Those two events cannot happen at the same time, so therefore that value is 0. So therefore you can say that the probability of A union B is simply the sum of the probability of A plus the probability of B for two mutually exclusive events. All right, let's talk about complementary events. Now, complementary events basically are two events that are the only two outcomes in your sample space. So think about ways that this can happen. So say, for example, we toss a coin. There are only two outcomes there. You're either going to get a heads or a tails. So tails is the complement of heads. There are only two outcomes. They make up the entire sample space. Another example would be, let's think about the complements of different events. What you can pass an exam or you can fail an exam. That's another example of complementary events. You cannot both pass and fail an exam. So the complement of passing an exam is failing an exam. Only two outcomes with complementary events. So the complement of any event, A for example, is the event not A. We write down the complement also as A prime. Since every element in the sample space is either in A or not A, the union of the complement covers the entire sample space. Now think about that. Really what we're saying here is because there's only two outcomes, either A or not A, if you combine those two things together, it will give you all of the outcomes. That should make sense. All of the outcomes. Pass an exam, fail an exam, it's the only two outcomes in your sample space. Okay. So since every element in A is not in not A, so every element in A is not in its complement, we know that complementary events therefore must be mutually exclusive. You cannot pass and fail at the same time. So therefore the intersection is 0. So all complementary events are mutually exclusive, but not all mutually exclusive events are complementary. Guys, this is an important idea. All complementary events are mutually exclusive. In other words, they've got no intersection. But not all mutually exclusive events are complementary. Think about cases where this happens. Say, for example, you are looking at a deck of cards. There's 52 cards in the deck, and you want to draw out an ace. But you can also draw out other cards. So say I want to also draw a 2. Let's look at drawing an ace and drawing a 2. Are those complementary events? No. Why are they not complementary events? Because they are not the only two possible outcomes. You can get an ace, you can get a 2, you can get a 3, a 4, a jack, a queen, and so on and so on. So they are mutually exclusive, which means you cannot get an ace and a 2 at the same time. Yes, they are mutually exclusive. They cannot happen at the same time, but they are not complementary. Okay, so complementary, again, I'm going to say it for probably the 5th time already. Complementary events cannot happen at the same time, and they are the only two possible outcomes in that sample space. So the probability of complementary events sum up to 1. So for example, if we're looking at the probability of A plus the probability of not A, that is equal to 1. Because there is no intersection, I can say that the probability of the union is then equal to 1. So therefore, if I then just rearrange this equation, I can get that the probability of A is equal to 1 minus the probability of not A. So the probability of A is equal to 1 minus its complement. Okay, and those are important formulae that well, it's not really a formula, it's something you should remember, but those are important concepts that you should remember for when you are calculating probabilities. Those concepts being the addition rule or the addition identity for events that are not mutually exclusive. Then we looked at the addition rule for mutually exclusive events, and then we looked at the formula for complementary events. All right, let's talk about Venn diagrams. So a Venn diagram really is just a representation of the relationships between sets. Okay, so in a Venn diagram, you will see that each event is represented by a shape. Often we use a circle. The area inside the shape, so I might have a circle here, and then another circle there, right? So the area inside the shape will show everything that's included in that event, and the region outside the shape will be all the events that are not included in your event that you are looking for. Often what we will do is we'll put a rectangle around those circles to show our entire sample space, pretty much like what's on your screen. So if we have two events, A and B, in a sample space, there are different ways that the Venn diagram can represent the possible outcomes of events A and B. So we can look at, in the first case, we have A and B intersecting. So these are obviously not mutually exclusive because they have an intersection. Then in a mutually exclusive or disjoint case where there's no intersection, you can see that A and B are two separate circles within your sample space that do not have an intersection. The other possible way that these two events A and B can interact with each other is that you might get the one event, for example B, completely contained within A. So the intersection of A and B is this whole set B. All right. So Venn diagrams are extremely important, especially when we're looking at multiple events happening, and we often have to answer questions on Venn diagrams, by interpreting the Venn diagrams, and then also by drawing the Venn diagram. So you need to understand the different ways that sets interact with each other and what the circles overlapping and not overlapping mean. All right. Another important concept that we deal with when we're looking at multiple events is tree diagrams. Now, tree diagrams are extremely useful when we look at a sequence of dependent events where the one event influences the outcome of the other, but we can also use them for independent events. So for example, if we toss a coin 4 times, that will have 16 outcomes, which can easily be shown on a tree diagram. The reason we call it a tree diagram, it looks like a tree. When we look at the diagram, the way I like to think about it is if you take that diagram I'm going to show you just now and you turn it onto its side, or if you turn it so that it's sort of facing vertically, as you'll see just now, it kind of looks like a tree. So each branch or arm in a tree diagram shows us an outcome of an event along with the probability. So let's have a look at this. Say, for example, we're tossing a coin twice. We're going to get a tree diagram that looks like this. So what you'll see is each of these arms represents your possible outcomes. If I toss a coin the first time, I can get heads or I can get tails. Along those arms, we then write down what the probability of each outcome is. So the probability of getting heads is the number of ways I can get a heads divided by the total number in the sample space. So the probability of getting a heads, I can either get a heads or a tail, so it's going to be 1 head over 2 possible outcomes, so it's a half. And that's what we write along the arms. The probability of getting a heads is a half, probability of getting a tails is also a half. Now when you toss the coin again, remember these are independent events, so when you toss it the second time, once again you can get heads or tails. The probability of getting a heads or a tail does not change because these are independent events. So therefore, once again, you will see along each branch or each arm, we will see that the probability of getting a heads is a half, probability of getting tails is a half. Okay, and this is what I'm saying. If you sort of turn the diagram over, this looks like a tree. So the possible outcomes, say you've tossed the coin the first time, you get a heads. You've tossed the coin the second time, you get a heads. So therefore, in 2 tosses of a coin, you can get a heads and a heads. And if I want to know the probability of getting a head and a head on 2 coin tosses, I simply multiply the 2 probabilities together because these are independent events. All right. So therefore, 0,5 times 0,5 will give me 0.25. And we can go down the tree diagram in the same way. Probability of getting a heads and then a tails would be 0,5 times 0,5, which is 0,25, and so on and so on. Remember, when you go down the arms of the tree diagram or across the branches like this, then the sum of the probabilities is always 1. Okay, it makes sense because it should represent all your outcomes. So you can see each time we're going vertically across the branches of the tree diagram, our sum will always be 1. Okay, so those events, in this case, first toss of a coin, we get 2 outcomes, heads and tails. Those events are mutually exclusive. If we take the sum down the branches of the arms of the tree diagram, we see that they sum up to 1. When we get our final list of possible outcomes, so say for example 2 tosses of a coin, we're getting heads, 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 tails, tails, heads, tails, tails. When you add all of those as well, going vertically in the last column, you will also get a sum of 1. All right, guys. Okay, so we've covered the main big ideas that you need to remember for your probability exam. Please let us know if you have any questions by doing your practice questions, and I will see you next time. Cheers.